This is section 13.5 about lines and planes in space. Most of calculus, when you did calculus 1, was about taking an object that was curvy or complicated and replacing it with a simpler object, its tangent line. Now that we're doing Calc 3 in more dimensions, we'll replace things with, well, it won't often be a tangent line, but some objects will have tangent lines, some objects will have tangent planes, some objects will have things called normal lines. So figuring out how to deal with lines and planes in 3 dimensions is a big deal. Our goal is we want to be able to just write equations for lines and planes, and then we want to be able to find the angle between things. A lot of what we do, it's hard to explain like how important it is to be able to figure out if 2 things are perpendicular. We take it for granted in 2 dimensions that you can tell if 2 things are perpendicular by like looking at their slopes. We need to be able to find angles between things in 3 dimensions, which can be kind of complicated when there's so many directions to go. At the end, we'll find the distance between some things, so just do some geometry with lines and planes. Okay, just to remember what we did in 2 dimensions that's the same thing as what we're going to do in 3 dimensions, is that if you know the slope of a line in 2 dimensions, then you can just write down the equation of a line like right away. You pick a point on the line, you drop the point into these slots, and then you put the slope here and you're all set. Now, the problem is in 3 dimensions, we don't have a number, like a scalar that's a slope. If I have some flat plane and I ask you, okay, what's the slope of the plane? Well, what do you mean the slope? Like it's kind of steep if I look that way, it's kind of like flat if I look that way. And so I don't really have a number. Instead, the slope of a plane will be given by a vector. So we'll have to use vectors. And it will turn out that we don't really get a slope. Like we won't be able to say, what's the slope of a plane? And the answer won't be a vector. Yeah. So let's just get the equation of a... I don't like the equation. I want like an equation of a line. So we'll do the same deal, like where we'll try to have like a point slope form essentially, but in more dimensions it won't work quite as easily. So let's start with a point on a line. And then when we have a line, we can actually give it a slope, which is which way is the line going. That's a vector v. And just to make the notation simpler, I'll call the vector ABC. Given these 2 ingredients, you can combine these together and just say like, okay, start on a point, start at the point x0, like the point P, and then go in this direction as much as you want. Like you could go in this v direction 1 time, or you could go in the v direction twice, or you could go in the v direction backwards once. The v direction will like tell you which way the line goes. So it's all the points Q such that PQ is parallel to V. Oh dear, let's get a picture of that. So here's P. Here's the vector V. And the line that we're talking about is this line. This is the line we're trying to write an equation for. To tell if a point is on the plane, or is on the line, what you could do is you could say, well, is PQ the same direction as V? This one, PQ, is not parallel to V. So Q is not on the line. Let's get a different color. If I pick a point that is on the line, now the vector PQ is just a multiple of V. So Q is on the line. So this is just a vector way of trying to say what a line is. You pick a point and a vector, and you say a different point is on the line if PQ is parallel to V. Okay, hopefully we can turn that into an equation. What we'll do is we'll say, okay, PQ is parallel to V. Let's let Q be the point x, y, z. And we already know that P is the point x0, y0, z0. Okay, what's PQ? PQ is a vector. It's the ending point minus the starting point. So we're going to have x minus x0, y minus y0, and z minus z0. And then parallel to v, parallel to, for vectors, means that it's equal to a multiple of. And then we'll put v here. V is A, B, C. I guess I can't really use C for the multiple. It's kind of like taken already. I've got A, B, C here. What will be a useful thing to think about is I'll think about t as my parameter. T like time. So at time 0, I'm at point P. At time 1, I've gone V over here, and this will be time 1. And so on. So this would be this can be my setup to try to make equations of the points on the line. If I get the x0, y0, z0 over to the right side, then I'll have x, y, z is, okay, what's this part? This part has, let's simplify this before we go forward. This is TA, TB, TC. So xyz will equal, well, I have to add x0 to the x component, y0 to the y component, and z0 to the z component. So I'll have x0 plus TA, y0 plus tb, and z0 plus tc. This is our equation of a line. Now, you could argue that this is actually 3 equations, because I've got an equation for x is x naught plus ta, an equation for y, and an equation for z. From that perspective, this is a set of 3 parametric equations. But it seems better to me to think about this as a vector-valued function, which we'll get into what that's about in chapter 14, but that you input t, and the output is a point here on the line. So this is the way to write a line as a vector, a single vector equation. If you write it in parametric form, you separate these out and you say what x, y, and z are. So this is parametric form. Nice. Oh dear. Here's a box for me to write what I just wrote. That's too bad. Okay, so the parametric equations of a line, the easiest way to do it is x is the starting point plus t times how much you're going in the x direction. Y is your starting y plus t times how much you're going in the y direction. And z is your starting z plus how much you're going in the z direction. If you write it as a vector, then the vector equation is x, y, z is the starting point plus t times the direction you're headed. So 2 different perspectives, same exact thing. Okay, so this one says here's 2 points. Just write an equation of a line between these 2 points. Okay, you pick one of them to be the base point. You had to do this even back in like pre-calculus when you had 2 points and you were trying to draw a line between them. You had to pick one to be the base point. It doesn't matter which one you pick, but I'll just pick this one. So x naught, y naught, z naught will be 2 minus 3, 1. And then ABC is the direction that the line is headed. And the direction vector you can find by doing the endpoint minus the start point. So I'll have Q minus P. So the direction vector is minus 3, 5, 3. If you combine these together, you can get a vector form of the line by saying, oh, well, a point on the line is given by the start point plus the amount of time you've traveled times the direction you're traveling. And if you simplify that, you'll get like 2 minus 3t, minus 3 plus 5t, and 1 plus 3t. So this is the vector form of the line. The parametric equations for the line are to say, I'm a little uneasy still with vector forms, so I'll think of this instead as 3 equations, one for x, one for y, and one for z. Because these equations have the parameter t in them, these are the parametric equations for the line. Anyway, the analogy back to the equations of lines in 2 dimensions was it's kind of like the same deal as what you had before. You've got like a number plus a number times a variable. The scalar that's by itself comes from the starting point, and the scalar that's attached to the parameter comes from the slope or the direction that you're headed. So like y equals mx plus b, this direction, the part from the direction is kind of like the m, and the part by itself is like the b, the starting point. You don't have access to maple, so I'm gonna skip the maple thing here. Okay, let's find the distance between a point and a line. So let's say you have a line somewhere in space. This will be the line. And we'll say that it's given in vector form. So it's got some starting point plus a parameter times a direction. And then, so we'll call this the line L. And then we'll say you have another point, Q, that's not on the line. And the question is, how far is it from the point to the line? I called it question mark. You're not like children. I can give it a name. Okay, so we'll say the distance from the point to the line is d, and I want to find d. Okay, what can I possibly do? Well, what you do is you take a point on the line, any point on the line, say call it P. This is choose P in the line. And then you go, okay, well, I can like draw, using any point on the line, I can get a right triangle on the picture. Here's the vector PQ, and here's a right triangle. Now you can say, oh, well, whatever's going on here, this angle is important, and the distance is just this length of the hypotenuse times sine theta. And theta is the angle between PQ and this direction vector V, because the direction vector V is headed this way. Okay, so what's going on? Well, we've got sine theta here. So we suspect that the cross product is going to be involved. And in fact it is. We can notice, let's do this in blue because it's a fact about V. We can notice that if you had crossed V with PQ, then you would get, by our formula for the cross product from the previous section, just the size of V, the size of PQ, times sine theta. This equation isn't right now because the right side is a scalar and the left side is a vector. This fact about the cross product is about the magnitude of the cross product. So the magnitude of V cross PQ is the magnitude of V, magnitude of PQ, sine theta. And if you just write down that formula and then look at the thing you're trying to find, you notice wait a minute, PQ sine theta is what I wanted. This is D. So this just gives us our formula for what the distance is. The distance between a point and a line is you pick a point P on the line, and then you find this cross product formula. V cross PQ, take its magnitude, divide by the magnitude of V. So we can write this down as a formula. The distance is magnitude of V cross PQ divided by magnitude of V. Unfortunately, just knowing this formula by itself is a little bit sketchy, because here this formula is the distance between Q and the line, where P is a point on the line. So you have to keep that straight when you're using the formula, like what's P and what's Q. So P is on the line, and Q is off the line. And V in this formula is the direction the line is going. Notice that I'm not saying the slope of the line. We're thinking of lines as having a direction vector. So you can use this formula to find the distance between a point and a line. I think we'll do an example. Yeah. Okay, so here's a line. It's in vector form. You've got an x component, a y component, and a z component of the line. And you can pick out the starting point. It's like the b in y equals mx plus b. It's the 7 that's by itself, the 2, and the 4. And the direction is the part that's attached to the parameter t. So the direction vector is 5, minus 1, 12. What are these called in the distance between point and line formula? This is the point P, and this is the direction vector V. And here's our point Q. So once you've, excuse me, once you've kind of like peeled apart the line to get all of its components, then you can just drop it all into the formula. The formula is that the distance between a point and a line is the magnitude of V cross PQ divided by the magnitude of V. So we just have to find all that stuff. Here's V. I guess I need to know what PQ is. You do the end point minus the start point. So Q minus P. So here's Q minus P. So PQ is minus 12, 0, 5. So I have to just find all this stuff and I'll get the distance. Well, V cross PQ we can do because we learned how to do cross products in the previous section. I've got I, J, K. V first, so 5 minus 1, 12. PQ is minus 12, 0, 5. I'll use the shortcut where I copy down the first two columns twice. Well, the first two columns once each. And then I go the forward diagonals first. So I'll have minus 5i, minus 144j, oh dear, 0k. And then I do the backwards diagonals, and those I get opposite. So this one I'll have minus 12k. This one I have no i's, and this one I'll have minus 25j's. So V cross PQ is minus 5, minus 169, minus 12. What a mess. Okay, so I'll need to find the magnitude of this and divide by the magnitude of V. So this is magnitude of V cross PQ, 169 squared, okay, divided by magnitude of V. This looks like these numbers have been chosen really carefully. I don't have any way to do this in my head, and I don't know any like trick to do this. Oh, I do. Okay, I think you should probably just put this in a calculator. There's no reason to do this, but part of the reason that you bother hiring someone who's like seen a lot of math is to see cool crap sometimes. So here's something cool. 5, 12, 13 is a Pythagorean triple, which means 5 squared plus 12 squared is 13 squared. So I can combine 5 squared plus 12 squared and make it 13 squared. Down here, I also have a 5 squared plus a 12 squared, but I'm going to put it this way. So I group together 5 squared plus 12 squared and make it 13 squared. Then I notice that each of these corresponding pieces is 13 times larger than its other one. So I factor out 13 squared from the numerator. So it all cancels and you get 13. To be totally clear, this last part, it's not really important. It's just like a cool trick, but you can just put it in a calculator and get the answer. The main thing is to figure out what the v, the p, and the q mean in this formula and practice using them. So p is a point on the line, q is a point off the line, and v is the direction that the line is headed. So that's it for lines, basically. We figured out how to make an equation of a line, and we figured out how to find a distance between a point and a line if the point isn't on there. So now let's deal with some planes. So what makes a plane in space? Well, you pick a point in the plane. Yeah, so you pick a point, like x0, y0, z0. And then to decide which direction the plane is oriented, so you pick a point, and then you say, okay, which way should I make my plane go? The way that you define which way a plane is oriented, you can't say, like, what is its slope. And you can't even pick a vector that says, like, which way the plane is going, because the plane goes lots of ways. Instead, you say, for a plane in space, there's one direction that the plane does not go. You pick a normal vector to the plane. Now, the words perpendicular, orthogonal, and normal, they all mean about the same thing, like a 90-degree angle, but you would normally say, normally? But you usually say that two vectors are orthogonal to each other, and if anything else is like at a 90-degree angle to some other thing, then you say that they're normal. So here I have a vector and a plane. Those are normal to each other. So this is called the plane's normal vector, and that's why it's called n. So perpendicular, like, fine. Perpendicular is mainly for, like, lines. Orthogonal is for two vectors. Normal is for weird objects. So, like, if you take your face and you point outward from your face, like at a 90-degree angle from your face, you would say that this pen is normal to your face. You wouldn't say that it's orthogonal to your face. So this is a normal vector. This is wrong. This is, like, okay, but let's do better. Normal vector n. Give it a name, probably ABC. Yeah, that seems fine. So to get an equation of a plane, you pick a vector that's normal to the plane. Then you say, oh, well, to write an equation, I can tell whether things are at a 90-degree angle to other things using the dot product. So you say, here's my plane, here's my base point, and here's my normal vector, n, that's, like, coming out of the plane. You can tell if a different point is on the plane, say a point Q, if going from the base point to Q is orthogonal to the normal vector. So you say the points on the plane are the ones where PQ is orthogonal to n. If you write that as an equation, it'll be an equation that has to do with the dot product. So let's say this is the point xyz. PQ is endpoint minus start point. I want this vector to be orthogonal to n. Notice when it's vectors, you say orthogonal, and when they're both vectors. How do you show that two vectors are orthogonal? You take their dot product and set it equal to 0. So you say x minus x naught, y minus y naught, z minus z naught, dotted with ABC is 0. The end result of this, if we multiply this out, actually do the dot product, is the easiest formula that we have to make an equation of a plane in space. So the dot product gives you a scalar over here, so there won't be any vectors anymore. We'll have a times x minus x naught, and b times y minus y naught, and c times z minus z naught. And this is all supposed to equal 0. The dot product adds up all of those products. So this is our equation of a plane. And we'll just put it in this box to show that it's like important and something that you need to be able to just recall. This is super powerful. To be able to write just one equation to get a plane is really nice. Getting equations for a line was tricky because we needed to either have vectors on both sides of the equation or we needed to have 3 equations with a parameter in it. Equation of a plane is actually easier than the equation of a line. And this is it. The main thing to remember is that these numbers, ABC, this is a normal vector to the plane. It's not a vector that like points which way the plane is going. It points which way the plane is not going. Let's do some stuff with this. So we'll say, here's a point, 2, 3, 0. And here's a normal vector, -1, 2, -3. The plane should be everything, it should be everything that doesn't go in the normal vector direction. So, I don't know. This plane. And a plane has one equation. So what is an equation for that plane? It turns out it's just really easy to write down. You set up this start. I didn't leave space. So you set up this start. Any plane in space can be written this way. Then the normal vector goes here, and the base point goes in here. The reason behind that was the picture I had on the previous page, but you don't have to use that picture every time. You need to be able to use this formula to quickly build the equation of a plane. Then you can simplify all this and you'll get a nice answer, or you can just circle it. Let's simplify this one a little bit just to show how these can end up looking nice at the end. So another way that a plane might look is you could combine all the numbers together and get all the scalars over on the other side of the equation. Here I've got 2 minus 6, so it's -4 on the left side, it'll be +4 on the right side. So here's another way to write the plane. Just to be clear, in most cases, this would also be an acceptable equation of the plane. That's why it's important to write an equation, because there's lots of equations for a plane, just like there's lots of equations for any one line. So let's find an equation for the plane that has the z-axis and this point. Ooh, interesting. Okay, so here's x, y, z. I pick some point, 3, -1, 2. And then I want a plane that goes through both this point and this line. What's a good way to draw this? When it's happening like in the real world, I can imagine how to do it. If I had like a point and I had a line over here, I would just take the plane and I would like connect them. I just put the point, like put a plane between the point and the line. I'm not finding a good way to draw it. Did I have one the last time I did this? No, my picture's terrible. Okay. I mean, I guess the plane should have this in it, so it should be like this way. And then the x-axis would like poke out of it. Like you wouldn't be able to see this part and it would like suddenly appear. I'm not sure we're really helping here. can kind of see it. Luckily, the picture is not really that important. Yeah. So how do we do this? We need to say, okay, well, to get an equation of a plane, we need to find a base point, which we've already got, and then we need to find a normal vector. If you can find a normal vector to the plane, then you can just drop everything into the form of a plane and you're just done. So this is your goal. If the question doesn't give you a normal vector, then you have to find one. Well, how do you find a normal vector? Well, one way to find a normal vector would be to say, if I could just find two vectors that were in the plane, and I took the cross product of them, I would get a result that was perpendicular to both. So plan, find two vectors in the plane, then if you want a vector that's orthogonal to two vectors, then you can cross them, and that will give you a normal vector. Why? Well, that's how the right-hand rule worked. We said, like, okay, you point at one, you point at the other, and then your thumb will point at the other one. Yeah. Okay, so we need to find two vectors in the plane. One vector in the plane is, well, the z-axis has a vector attached to it. Whoa, z is not a vector. The z-axis tells you that one vector that's in the plane is the one that points in the direction of the z-axis. What else? Well, we've also got this point in the plane, the origin, and this point in the plane. So here's another vector that's in the plane, the vector that goes from the origin to this point. I have two vectors that are both in the plane, so if I cross them, and in this case I'm gonna do u cross v, so like the fingers of my hand will point toward u, I'll curl toward v, and I'll find that I'm expecting to get a normal vector n that will like point this way. To do it, I just do the cross product. Well, here's the cross product of u and v. I'll use the trick where we copy down the first and second columns because I like it. All these zeros will be very helpful. When I do the forward directions, I get 0, 3j, and 0. When I do the backward directions, I get 0, minus I, and 0. So I get 1, 3, 0. Which seems like kind of like what I drew, actually. A little bit in the x direction and a lot in the y direction. So wait, what was, oh, well, this was our goal, apparently, was to find n. So yeah, this works. So then since I have a base point and a normal vector, I can just drop it all into my equation of a plane. Equation of a plane looks like x minus a thing, y minus a thing, z minus a thing equals 0. The normal vector goes here, and the base point goes in with the xyz. 0 times z minus 2 we can get rid of. So my end result will be x minus 3 plus 3y minus 1 equals 0. So this is my equation of a plane. If the question says that you have to like simplify, which it normally won't, but if it does say that, then you could multiply all this out. And I guess I'm gonna have x plus 3y, ooh, I copied this down wrong. So x minus 3 plus 3y plus 3, the 3's actually cancel. So simplifying it here was definitely worth it. So the equation of this, n equation of this plane is x plus 3y equals 0. Just to check this, if you did this right, the point that you started with should actually satisfy the equation. Otherwise, this is really nonsense. And it does. If I do x plus 3y for this point, then I do get 0. So what's the takeaway from this? Well, to find an equation of a plane, you need a base point and a normal vector. If no one gives you the normal vector, you need a way to find it. And the easiest way to find a normal vector is with a cross product. Okay, here I've got 3 points. Well, how am I going to find a plane with 3 points? I don't want 3 points. I want a point and a normal vector. So here's my points. 1, 3, 2, 0, 0, 5, and -2, -2, 3. At this point, I've given up trying to draw them in 3 dimensions because I don't gain much from that. What I do gain from is realizing that these 3 points, if they're all in the same plane, I'm looking for a normal vector. And to find a normal vector, I need to find 2 vectors that are in the plane and cross them. Well, finding 2 vectors in the plane is no problem. Here's one, and here's another one. And there are a bunch of other options, but you just pick 2 vectors that are in the plane and aren't the same, and cross them. U here is the vector that goes from 132 to 005. So we'll need to go, how do we get from 132 to 005? X goes down by 1, Y goes down by 3, and Z goes up by 3. And then V is how do we get from 132 to, I don't want to think about that. I like 005. 005 is great. Let's use 005 again. I want positive numbers. Notice that you get choices, and as a result, you can like make the choices to make your life easier. So when I go from -2, -2, 3 to 005, X goes up by 2, Y goes up by 2, and Z goes up by 2. So I made the choices to make my life easier. Now I cross these 2 vectors. All these 2's. Okay, the forward direction, I get -6i, 6j, whoops, oh no, okay, 6j and -2k, and then in the backwards direction, so I'm going to have to subtract all this, I get -6k, 6i, and -2j. So in total, what's my normal vector? My normal vector is -6, -6i, so that's -12i. 6 minus -2, that's 8j. And -2 plus 6, that's 4k. Now, a thing you should notice here is that the normal vector, there's lots of normal vectors to a plane. This particular normal vector, it has like larger numbers than are necessary. Any normal vector will work. So this normal vector is like, it's like this direction, but it's like 4 times as long for no particular reason. If you ever have a normal vector and any normal vector will do, then you can just scale it down. So I'll make a second normal vector where I scale it down by 4 just to make my life easier. -3, 2, 1. So I took my original normal vector and I scaled it so that my final answer would be simpler. Then I can put it all together into an equation. So I'm going to have the x's, the y's, and the z's all add up to 0. The base point goes in with x, y, z. I can pick anything to be the base point. So I'll pick the easiest one, 0, 0, 5. And then the normal vector, I've made an easy normal vector for myself, -3, 2, 1. So my final answer, I'll have -3x plus 2y plus z minus 5 equals 0. And if I add the 5 to the other side, then it will look like this. So here's an equation for my plane. If I did this right, all these points should work in this equation. So like 0, 0, 5 certainly works. I used it as the base point. How about 1, 3, 2? If I plug in 1, 3, 2, I get minus 3 plus 6 plus 2 equals 5. Yep, that works. So the goal is to find our normal vector. A normal vector can be found by crossing any two vectors in the plane, but there's infinitely many choices of vectors in the plane, so pick the nicest ones you can find. Then once you get a normal vector, if it's super unwieldy, just scale it. The scaled copy of a normal vector still points the same direction. If you don't scale it, it's totally fine. You'll just have to like divide by 4 at the end, but whatever, it's okay. It's just, yeah, I'll just always try to show you ways to make your life a little bit easier. Okay, so we figured out how to make equations for lines and equations for planes. Let's just figure out a couple of important planes, and then we'll try to do some more geometry with them. So the xy plane is all the points where z equals 0. You should notice that this shows you a normal vector. The x's got killed, the y's got killed, and the z has a coefficient of 1. So a normal vector for the xy plane would be, if you're in the xy plane, a normal vector points straight up. Similarly, the xz plane is y equals 0, and the yz plane is x equals 0. Okay, let's get an equation of a plane that's parallel to the xy plane. Parallel to the xy plane means that it has the same, it's going the same direction, so it has the same normal vector. So what else could you have with this normal vector? I mean, you're stuck with 0, x minus something, 0, y minus something, 1, z minus something equals 0. Like, where are some choices that matter? Like, it doesn't matter what you put in here, it's getting zeroed. It doesn't matter what you put in here, it's getting zeroed. So your only options are to put some constant here. Okay is such a bad choice for a constant. I guess I'll use c. So the planes that are parallel to the xy plane, the only thing you could do is just put a number here. So you'd get z minus c equals 0. These are the planes that are parallel to the xy plane. Z equals a scalar. That makes sense. The xy plane is a flat plane. If you went like up here, then it would be parallel. Okay, so how can you tell if two planes are parallel? Planes are parallel if they have the same normal vector. Do they have to have the same normal vector? I guess they don't have to have the exact same normal vector. They just have to have normal vectors that are pointing in the same direction. But the key thing here is that if you want to compare planes or compare lines, you kind of boil down their orientation into one direction. So a line, you have like the direction the line is going. For a plane, you have a normal vector for the plane. And either way, you're like reducing all your geometry questions down to questions about vectors. Two planes are orthogonal. No, planes aren't orthogonal. Planes can be normal to each other. That feels wrong to me too. It feels like planes should be perpendicular because they're both geometry objects and neither one is a vector. But now I'm not sure. I know orthogonal is bad. Okay, how could we tell that? Well, if you look at their normal vectors, two planes will be perpendicular to each other if their normal vectors are perpendicular. So basically you take an object, and if you want to know if object is geometry related to object, you go like, that's nice, I'll look at the vectors instead. And that will give us our fact here in the box. So two planes are parallel if their normal vectors are parallel. And two planes are at right angles to each other if their normal vectors are orthogonal. Notice that my first guess at how do you make two planes be parallel was that they have the same normal vector, but no, it doesn't really matter if they're exactly the same, they just need to be going the same direction. So if their normal vectors are parallel, then the planes are parallel. Okay, let's just do some complicated stuff here. So let's try to find the equation of a line that you get when you intersect two planes. So we've got the plane Q is 2x plus 3y minus z equals 6. And here's another plane, Oh, did I write q equals? Blah. The plane doesn't equal 6, so that's a disaster. The plane is given by this equation, and here the plane is given by this other equation. So we have these two planes, and if you have two planes, you would expect them to either be parallel or they would intersect, and their intersection would be a line. So this question is asking, like, that's nice. Where is this line? When you are trying to do geometry with objects in more dimensions, you should imagine that the only way forward really is to deal with the vectors that tell you which way those objects are pointing. So here I have the normal vector for the plane Q is, and you can just pull it off of the equation, 2, 3, minus 1. And a normal vector for the plane R is 1, 4, 2. These normal vectors tell you which way the planes are oriented. These normal vectors aren't in the planes, but yeah. Okay, so what are we looking for? We're looking for the one direction, like the one line, that these planes have in common. Here is the direction that Q does not go, and here's the direction that R does not go. So it has to be whatever our answer is. So our line has to be perpendicular to NQ, because it's NQ is normal to the plane. So we're looking for something that's in the plane, so it would be perpendicular to NQ. And our line would also be perpendicular to NR. How do you get a vector that's orthogonal to both of two other vectors? The answer is, if you want to be orthogonal to two vectors, you take the cross product of those vectors. So this will be my direction for our line. I'll just take NQ and cross it with NR. That manufactures a vector that's orthogonal to both of these vectors. So let's do it. I, j, k, 2, 3, minus 1, 1, 4, 2. I'm going to copy down the first two columns. The forward direction, I get 6i, minus j, and 8k. And the backwards direction, I get 3k, minus 4i, 4j. So in total, I have 6 minus minus 4 in the I direction, minus 1 minus 4 in the j direction, and 8 minus 3 in the k direction. So here is a vector that goes in the direction of my line. Just like before, if all you really are picking out is the direction, then you can scale it up or down to make your life easier. So this will be our direction for our line, is I'll take this vector and I'll scale it down by 5, because those all have 5 in them. So we'll go in the direction 2, minus 1, 1. What do you need to get the equation of a line? I mean, all I've done so far is I've found the direction the line is going. Well, what you need is you need a point on the line. So I have a direction. I need a point. So I need a point that satisfies both 2x plus 3y minus z equals 6 and x plus 4y plus 2z equals 8. If you try to solve this as a system, you'll find that there's infinitely many solutions because you have two equations with 3 variables, which means you get a lot of freedom in what the solution is. There will be infinitely many options. In particular, you can just take any one of these variables and be like, I declare that x equals 6. And there's probably a solution where x equals 6. You might get really unlucky and miss, but there are infinitely many answers. So in this situation, you're very likely to be okay if you just guess one of the numbers and then solve for the others. So a common thing to do is to just let z equals 0 and see what happens. I'll try y equals 0 and see what happens. The key here that lets me just declare that y equals 0 is that I have 3 variables and 2 equations, so I know there's infinitely many answers. Once I declare y equals 0, I can like solve for a variable and substitute it into the other equation. Then I end up with one fewer equation and one fewer variable. So this is 16 minus 4z minus z. So this is 16 minus 5z equals 6. And you can make that happen with z equals 2. Then with z equals 2 and a formula for x, you can find that x is 8 minus 4. So x is 4. So we found a point on the intersection of the planes. The point was x is 4, z is 2, and we declared y is 0. This is a point. This is not a vector that's giving us a direction, so it would be really bad to randomly scale this one because it would move the point. That's why it's important to tell the difference between like a vector and a point to decide whether it's okay to scale it depending on the situation. So how do I combine these together? Well, I have a direction and I have a point. So I can combine those together to get an equation for the line. I am completely out of space. I'll write the equation in vector form, and I'll just write it up here. It's the base point, 4, 0, 2, plus a parameter times the direction that we're headed, which was 2, minus 1, 1. So my final vector form of my line is 4 plus 2t minus t, 2 plus t. For any value of t, you'll get a point on the line. That's a neat problem. What are the like techniques that you have to take away from that problem? The first thing is to know what you're looking for. If someone asks you for an equation of a line, you need a point and a direction vector. So that like split my work up into 2 pieces. If you're looking for a direction vector, look at what you know about the direction vector. If you're looking for something that's orthogonal to 2 other things, you can use the cross product of those 2 things. If you're looking for a point, well, that's old algebra stuff, and you have old algebra techniques to use to try to find an intersection point. You may not remember, or you may not have become expert at this in pre-calculus, that if you have infinitely many choices, and you only need one of them, you can just like plug something in, and it usually works. If this didn't work, I would have tried x equals 0. Then at the end, you have your equation of a line or your equation of a plane. Okay, just a couple last final things here. So from pre-calculus, how do we get a horizontal line? A horizontal line in pre-calculus was like y equals a number. And a vertical line was x equals a number. Like, why did that happen? Well, all of the points that on a horizontal line had the same y value. But this is frustrating for pre-calculus students because that means that the x-axis doesn't have any x's in its equation. So to pre-calculus students, this just seems completely unfair that like the y-axis is at x equals 0 and the x-axis is at y equals 0. But what you can think of is now that you know that lines... Well, now that you know that like a single equation like this, that you can pick out a normal vector from this kind of equation, you can say, oh, well, y equals c has to be horizontal because the normal vector to this object, there's nothing in the x slot and there's 1 in the y slot. So whatever this object is, this horizontal line, its normal vector points this way. And the one that has x equals a number, this normal vector goes in the x direction. So this is another way to see why like a vertical line must have x equals, because a vertical line has a normal vector that goes in the x direction. This would like brutally injure pre-calculus students if we told them this, so we just don't tell them. So I'm sorry if you're like, oh, okay, why didn't you tell me before? The reason is like it would have gone poorly. So x equals 2 in 3 dimensions x equals 2 tells you that the normal vector to this plane is 1, 0, 0. So this plane, like the x-axis, is normal to it. I mean, it has x equals 2, so I'll have to come out here. But its normal vector points this way, down the positive x-axis. So I'm going to be this way, where all this stuff is in the background and the x-axis like pops out. This is x equals 2. And looking at x equals 2, you can think of it as all the points where x is 2, or you can now, after this section, think of it as, oh, that gives me a normal vector, and that normal vector is 1, 0, 0. It's the coefficients of x, y, and z. Y equals x squared. This is not a flat surface. This is not a line or a plane, so I can't use this kind of logic where I'm picking out normal vectors to find y equals x squared. Instead, y equals x squared is going to be some kind of like, it's going to be a bunch of parabolas stacked on top of each other in a smooth surface. Like this. So just be careful that, first of all, you become more powerful and think about direction vectors and normal vectors as being really useful. That's really good. But also don't extend that into situations where it doesn't work. So you can't use a normal vector, but you can't pick a normal vector out of the equation y equals x squared, but you can from this. Okay, there's a lot in 13.5. You need to practice a whole bunch of it. So go do some practice problems. Ask me some questions.